Okay, so let's continue our discussion of this quantity entropy. We had looked at how to predict the qualitative change in entropy. So we know that if a substance is at a higher temperature versus a lower temperature, its entropy would be higher. A gas would have a higher entropy than a liquid. A liquid will have a higher entropy than a solid. A dissolved solution has a higher entropy than its solute and solvent separated, except when we're dealing with a gas, where a gas is actually loses its entropy when it's being dissolved. And then lastly, we talked about the idea of atomic size and complexity, assuming that we're discussing things that are in the same state of matter. The more complex that molecule is, meaning the more bonds it has, it's going to have higher entropy. And then if it's a larger molecule, it's also going to have higher entropy. What I want to talk about now is how to put these qualitative ideas into quantitative values of entropy, right? Actually getting the numbers that correspond to the value of entropy. And to do this, we're going to need to talk about something called standard molar entropies and the third law of thermodynamics. So in the second law, we have discussed the idea that for all spontaneous processes, the change in entropy has to be positive. Now, the question is, how do we calculate that change in entropy? So if we have a reaction, A goes to B, for example, want to know if that reaction is spontaneous or not, we have to have a way of either measuring or calculating the delta S of that reaction, which is its change in entropy. Now, to actually measure delta S is possible. It's just that it's a laborious process. Typically, you're going to do some type of calorimetry at very low temperature in order to get the value of entropy, and usually you have to do a series of this experiment. Ideally, we want to do this an easier way, and the easier way could be done if you're looking at that same reaction A goes to B by just calculating delta S using S final minus S initial. Since we're talking about a reaction, our final state is the product, our initial state is the reactant. We just want to know, is that reaction spontaneous or not? So that means we're just taking the entropy of the product minus the entropy of the reactant. Now, for us to be able to do this, though, we're going to need to have numbers for the entropy of the products and reactants. And these are what we call absolute entropy value. They're not the change in entropy, but they're the actual entropy value of that particular substance. In other words, if I have HCl, what is the entropy of HCl? I'm not talking about the change in entropy from HCl going to something else or something going to HCl. I'm just talking about HCl itself. What is its microstates at a given pressure, temperature, concentration combination, right? That's what we refer to as the absolute entropy value of that substance. How do we get these absolute entropy? Well, we know that we can calculate the change in entropy, or delta S. The question is, how do we use that method to calculate absolute entropy? Delta S in itself could always be calculated using this expression. And again, this is something I brought up before. It's the integral of the heat that's delivered reversibly in a process divided by the temperature. Okay, how do we use this expression delta S to help us get the actual S itself? Delta S is S final minus S initial, right? So let's say we know our final position is where that HCl at 298 Kelvin, 1 atmosphere, and 1 molar. So we want that to be our final condition. And we just want that number. We just want that S final for HCl. Well, we can get that number if we make our S initial 0, right? So in other words, our delta S is going to be the same as our S final if our S initial is equal to 0. So then the question becomes, what is a condition that would make a substance or a system has 0 entropy, meaning that it has no molecular motion, no disorder, everything is just in one microstate, okay? Well, the only possibility is if everything is completely stopped. Nothing's moving. And that happens at 0 Kelvin. And this is, in fact, what we actually call the third law of thermodynamics, which is that the entropy of a perfect crystal at 0 Kelvin is going to be 0. And this is how we can then use to help us determine entropy at some other condition. Because experimentally, we can do it as follows. We can start with a crystal of a particular substance that we're interested in. Again, so let's say HCl or NaCl or sugar or whatever it is we want. We started from 0 Kelvin. When we start at 0 Kelvin, we can assume the entropy of that system is 0, okay? Because of the third law, right? And then what we'll do is we'll heat the substance all the way to the desired temperature. That could be 298 Kelvin or whatever it is that we want. And then what we're going to measure is the change in the Q, right? Q is heat, but remember that Q can be expressed as C, the heat capacity, times delta T, right? And in fact, that's what I wrote here, Cp dt. Cp here just refers to the heat capacity at constant pressure. And then we have that Q over T, and so the T is at the bottom here. So the top there is just Q, that's C times D. And so we're able to get a value as a result of that. That actually is just a function of, again, the temperature that we're running this experiment in. So I'll just show you an example of that calculation. It actually looks like the plot on the left here. So here we're just calculating Cp over T as a function of temperature. And so let's say we're taking it all the way from 0 Kelvin to 298 Kelvin, or in this case to 300 Kelvin. So all that area under the curve here will correspond to the entropy value for that particular substance from 0 Kelvin all the way to 300 Kelvin. So now we have an actual entropy for that substance. Of course, when you go through from 0 Kelvin all the way to 298 Kelvin, a lot of times you go through different phases. It's not just one phase, not like all gas or all liquid or all solid. It's a couple of phases. So when that happens, you're going to need to break down these calculations in different parts. So this is shown on the right here. So the part that are corresponding lines here, these are your Cp dt over T calculation that I was showing earlier. So the integral of that. And again, we're not doing the calculation. I'm just showing you how we're able to get these numbers, okay? But then we have these parts here that are dotted, and that's the phase change part. So for the phase change calculation, you can also calculate the entropy of a liquid becoming a gas, for example, at constant temperature. And that calculation is done by taking the value of the change in the enthalpy of the phase change. So whatever the vaporization enthalpy is, we can take that and then just divide it by the boiling point of that particular substance. Okay, so in total, if you were to add all your integral of Cp dt over T expression plus all your delta S for the phase changes calculated using this formula right here, you're then able to get the S, the actual molar entropy of that particular substance. I want to emphasize that we're not doing any of these calculations. This is just to explain to you how these numbers are obtained. Once we get these numbers, life becomes really easy, because now anytime we're given a reaction like A goes to B, we want to calculate a delta S. All we need to do is find the molar entropy of B, molar entropy of A, and then just subtract one from the other, and we're able to get delta S, okay? So that number that we just got, that S, usually we put a degree symbol on top, and if you recall thermochemistry in Chem 11, this refers to the standard state, which is a specific condition of an experiment, just so that everybody is using the same reference state. Okay, so that's at pressure equal 1 bar, which is close enough to pressure equals 1 atm. Okay, so if you're more comfortable with the atm unit, then just keep that in mind, that these are experiments done at pressure about 1 atm. Temperature is usually 298 Kelvin for these type of experiments as well. If you want to look at values of S, you can find one from University of Wisconsin, has a link to this. I linked it to the lecture note. You can click on that and just take you straight to the values of S and other thermodynamic values as well. But at this point, we're just going to focus on the column that is marked S, okay? So I just mentioned to you the value of absolute entropy that you can get at that link. So this is the actual table itself. I just want to point out that right now we're only focusing on the value of absolute entropy, which is the one given in purple. Okay, so that's the middle column right there. You can see it says S with a degree symbol, which just means standard state absolute entropy value. And this is given per mole, so that's why it's called molar entropy. Unit is joules per Kelvin per mole. And so you can see that the entropy value, and again, focusing on the ones in the middle, almost all of them are positive, and that should make sense to you, right? Remember the experiment, we're starting from 0 Kelvin, and then we're going to an ending temperature, which is usually 298 Kelvin. That's the experiment that we do. And so we would expect entropy to go from 0 in the perfect crystal state at 0 Kelvin, all the way to some non-zero number, but entropy always increases. So that's why all the numbers, if you look through them, are positive. There are some negative numbers, not very often, but we do see some negative numbers. And if you look at what the negative numbers correspond to, they tend to correspond to ions in the aqueous solution. So there's one right there for hydroxide, -10. And then there's a couple of these for calcium and carbonate. Again, they're both all ions. So the reason why those ions have negative entropy value is because it's not really possible to do the same type of experiment that we just mentioned, where we take something to 0 Kelvin and bring it all the way to 298 Kelvin with ions. Ions cannot be separated. They can't be measured independently like that. We can do it with compounds, we can do it with solids, liquids, we can't do it with ions. So the reference point for ions, therefore, is not actually the 0 Kelvin state, but we actually define 0 for ion as the entropy of the H plus ion, proton, and that's just arbitrarily defined as 0 joules per Kelvin. Okay, because H plus actually is a fairly high entropy state, right? It's just H plus ions moving around. So there's some entropy associated with that state. So if my ion is something that doesn't have as many microstates compared to the H plus, then when I'm measuring relative to the H plus, I'm going to get a negative value. And that's why you see some of those negative numbers in the thermodynamic table that I was showing you earlier. All right, so the whole point of doing this is to use value of S to calculate delta S. So now, if we're given a chemical reaction, we have reactants goes to product, all we need to do is apply this formula right here to calculate the delta S of the reaction. We just take the sum of the number of moles of the product times the absolute entropy value of the product minus the sum of number of moles of the reactant times the absolute entropy value of the reactant. This equation should look pretty familiar to you because you've used it in thermochemistry in the context of delta H. So remember that we had used an equation that looks like this. Delta H of reaction is the same as the sum of number of moles of product times the delta H of formation of the product minus the reactant component times the delta H formation of the reactant. So I just want to remind you that that's the same exact equation, is just now being applied to entropy. Let's actually do this in a problem. We're given, in this case, the combustion of a mole of C3H8, and we're being asked to predict the sign of delta S and calculate the value of the actual combustion of C3H8. So let's take a look at how we solve that problem. First, we're going to start with actually writing out the combustion reaction itself, right? So we were told C3H8. You want to remember some information from your prior chemistry class, right? When we do combustion, we're reacting something with oxygen. And since this is a hydrocarbon, we're producing carbon dioxide and water. And the reaction itself is given, and it's also balanced for you already. So it's right there. In this case, the first question that was asked was just to predict the sign of the delta S for that reaction. So here's our combustion reaction. We see that everybody is a gas. Usually if there's a difference in states, we can make that prediction based on state. So the next thing we look at is just what about the number of particles? Who has more particles? Who has fewer particles? Well, it turns out that the one on the left has 6 particles, whereas the one on the right has 7 particles. So that means that we're going from fewer particles to more particles. The more particles you have, the more microstates you can have. That means the higher the entropy will be. So in this case, we would predict that our delta S is going to be positive because it's going from fewer to more particles. This was something that we did before in the prior section. Now that we have our absolute molar entropy, we can actually calculate the delta S value. We don't just say it's positive, we can actually find out what the number is. So to do that, we're going to apply that formula that I was just telling you about with the S of product times its number of moles minus the S of reactant times its number of moles. So we're going to apply it to this equation. In this case, I'm going to have 3 moles times the absolute entropy of carbon dioxide because the coefficient of the carbon dioxide is 3, and then plus 4 moles times the absolute entropy of water in the gas state. That's because those both are the products, minus, now we're going to go back to the reactant side, 1 mole times the absolute entropy of C3H8, which is called propane, and then 5 moles times the absolute entropy of oxygen gas. So to get those numbers, I go back to that table I was showing you earlier. I'm not going to actually go back and find this. I already found the numbers here. So for CO2 in the gas state, the absolute entropy value is 213.74 joules per mole Kelvin. For water gas, it's 188.825. For the propane, it's 269.9. For oxygen, it's 205.138. And then so I multiply each of those with the coefficient that I have, right? And in the end, I get a number, and that number is 100.93 joules per Kelvin, which is matching with my prediction. Remember, I predicted that it's supposed to have a positive change in entropy, and indeed what I get is a positive 100.93 joules per Kelvin. So that's how you actually calculating the value of the delta S itself.